All right, thank you very much. First of all, I would like to thank organizers for giving me the opportunity to present here, and I apologize not to be in person. I have recently moved to the Institute of Photonic Sciences, ICFO in Barcelona, and I started my new job just a few weeks ago, so I had to be here. All right, so let me start right away showing an image that motivates basically the research my group and I have been doing for several years now. And this is this image here, where we see a little dot in the middle. Sometimes people might think that this image shows an atom or an ion or a gas of atoms, a BC, but in this case, it shows actually a glass nanoparticle. So a piece of silica made of around 100 nanometers in an experiment in the group of Marcus Vermeyer in Vienna. And what is nice about this object is that this is relatively large for these sizes. This has around 1 billion atomic mass units. And in the image, we see here the particle well localized in a point of space. So, of course, we know that according to quantum physics, in principle, this particle should be able to be prepared in a delocalized state, even in a superposition state. And that what motivates our research is to think how we can prepare these nanoparticles into delocalized and superposition states. And eventually, of course, in the context of this conference, it will be interesting to see if these objects can be so massive that the gravitational field they generate is not negligible and can be measured and can be used to entangle other particles. And of course, with the idea of seeing what is observing experimentally, what is the interplay between gravity and quantum mechanics at this scale. And also to motivate this a bit more in the context of this conference, I would like to mention that actually we started to be interested in this topic, from the beginning when we started to think about preparing superpositions, and already back there in this paper where we analyze how to prepare superpositions of superconducting microspheres, namely to go to bigger scales. We started to discuss this idea that maybe you can see, enter into or defining a regime where maybe gravitational fields enter into place. And of course, I want to acknowledge Marcus Spermeier and his team, who gave a talk on Monday, with whom we have been working for many years and having a lot of discussions. So in this context, in that paper, we introduced this time scale. Okay, that's a time scale tau g that you can define, depends on h bar and g, and then it depends on the mass and the radius of a particle. This is if you want a definition here. But what is interesting about this definition is that actually, of course, this coincides first with the lifetime of a superposition predicted by Penrose. If this superposition would be larger than the size of the particle, this is exactly the tau g, which to some extent, using a dimensional analysis, you almost end up with that. That's pretty nice, this time scale. This is for the case in which you don't assume any mass resolution. And so this is just full superposition. Then these collapse models from Penrose and Dioschi predict that the lifetime of such superposition will be given by tau g. At the same time, we know that, of course, this superposition or this time scale also appears if you want to entangle now two masses that are delocalized by an amount delta x, then the entanglement time scales is given by tau g times this factor here, which is typically much larger than 1, which is the radius of the particle and the delocalization distance squared. Okay, so therefore one could define this gravitational quantum regime as the regime in which this timescale tau g will be much shorter than any other coherence timescale for these quantum states, because this is what you need in order to, for sure, falsify this prediction by Penrose and others, and also potentially entangle. Okay, so of course, when this delocalization distance is of the order of the 0-point motion for these massive particles, this ratio is huge, and therefore the entangling rate is highly reduced. So, but what is also interesting is, of course, to plot this tau scale in terms of mass. This is this red line here, and then you see that, of course, for masses below 10 to the 10 atomic mass units, these time scales is of order of million of seconds, so no way this could be smaller than any coherence time. But as soon as you go to masses to the regime of 10 to the 12 to 10 to the 16, which is between 3 to 6 orders of magnitude smaller than the Planck mass, then this time scale starts to be below the second, maybe approaching milliseconds and so on. So in that sense, one could consider that these are promising time scales to start to do quantum experiments there, right? But as we said before, to entangle, there is this additional prefactor of radius over delocalization distance, which is really large, that even enhances this time scale. So, of course, the potential idea is to delocalize the wave function to enhance the entangling rate. So this is what we discuss here, where you delocalize the wave function, and then you have the decoupling rate G is enhanced by eta squared, where eta is how much you delocalize, right? And to some extent, this is an idea actually we already used in some of the first works where we proposed to do superpositions, where we use this delocalization to enhance the nonlinear coupling to a cavity that was used to prepare superpositions by performing an X square measurement. So this is just, I wanted to put a bit this into context from where we come in terms of being interested in these ideas. But now recently, together with the groups of Marcus Aspermeyer and Lucas Novoni and Romain Kidan, we are really focusing on trying to find ways to prepare macroscopic superpositions at these masses and scales here. Okay, this is an European project we have in collaboration with these teams, also in collaboration with Tracy Northup, with the idea to try to push the experiments in which you can prepare macroscopic superpositions, so namely superpositions delocalized over large scales, few orders of magnitude more than the current record for the experiments of Marcus Arndt, who has given a talk this morning. Emphasized here, this is really experiments where you delocalize over large scales. So that's why here we don't list the optomechanical type of experiments where you have much bigger masses, but the small delocalizations. So what I would like to present is then just a quick summary of the control techniques that have been developed to do these things. Then, of course, briefly discuss the aspect of the coherence, which we know is key to be able to delocalize the states over large scales. I always like to show this image because if you think about the Schrödinger cat state, if you have an infrared camera, of course, you know whether the cat is dead or alive, because if the cat would be unfortunately dead, this picture would look very different. And finally, from this control and the coherence, I would like to present a very recent proposal that we have published, where we are pretty excited as we think it seems promising for preparing these superpositions. Okay, so regarding control, I think you have had already some talks about that. The key aspect is optical tweezers invented by Arthur Ashkin to trap polarizable particles even in vacuum. He actually did that in the 70s with microdielectric particles. This triggered optical trapping and control of neutral atoms. Many years passed, and now we are interested again on these nanoparticles that Ashkin was trapping back in the 70s. And the interesting thing is that once you optically trap a particle with a laser in high vacuum, you basically have a 3D potential. And the important units of this dynamics here is the mass of the particle, 10 to the 10 atomic mass units, the radius, and the trapped frequencies here, which are typically 100 kilohertz. And what is nice is that, of course, we know that if we cool to the ground state, then the center of mass would be delocalized over a very tiny length scale given by the quantum harmonic oscillator unit length. And for these numbers, this is around 10 to the minus 12 meters, so much smaller than the size of an atom, which is equivalent to a center of mass temperature of microkelvins. And it's cool to emphasize that while the center of mass is extremely localized in space, this object is still hot. Okay, so actually, at least in room temperature experiments, the internal temperature would be 300 kelvins at least, which is nice to think you have an object that is 300 kelvins hot, but its center of mass is really as cold as microkelvins, so basically almost 8 to 9 orders of magnitude difference in temperature, and they don't talk to each other. Okay, and that's pretty interesting to see. And while this looked always challenging, now this is possible experimentally. So the first experiments were done in the group of Marcus Aspermeyer, where they cooled the particle with a cavity by using scattering of the light from the tweezer into a cavity using the technique of coherent scattering that is known in AMO. And then also experiments were done without cavities, just measuring very well the scattered light so that you can know where the particle is moving to, and then apply feedback forces with electrostatic fields. And this is now kind of state of the art. So this is possible now experimentally since few years, both in one-dimensional motion, two-dimensional, and it should be possible potentially also to cool the three-dimensional motion. So that's the starting point. But as we said in the beginning, we want to be localized to larger scales, right? So, and the figure of merit is that's the starting point. Now we want to create wave functions that are larger and coherently expanded in units of 0-point motion by a factor larger than 1. And this is our figure of merit, eta. And ideally, we would like to go to delocalizations of the order of 100 nanometers, which is the size of the particle, or even more, right? So note that in this line here, I increase the wave function by 5 orders of magnitude, and this is not to scale, right? And I like to emphasize that when we mean delocalization, quantum delocalization, of course, this means motional squeezing or quadrature squeezing in phase space. Because if you represent the state of a one-dimensional moving particle, you can describe a phase space distribution that in the quantum version is the Wigner function. And if you expand coherently, it means you don't increase the area of the phase space distribution, therefore you must squeeze, okay? And here is an animation, this we do in, it's nice to remember, this is the typical exercise of quantum mechanics first course, where you look at the free dynamics of a wave packet, okay? Just Hamiltonian p squared over 2L. So we know that the wave packet expands linearly in time, but if you look at the phase space distribution, then that's the dynamics. You see that the probability distribution in X grows linearly, but of course the momentum distribution does not change because momentum commutes with the Hamiltonian. Therefore, since this must be kept constant while you grow, you must squeeze a lot, okay? Because now the orthogonal direction here would be actually very squeezed. And this is really variance or quadrature squeezing. And therefore, it's nice to remember that when we say, okay, we are gonna squeeze, no, starting from here, then if we prepare states of the order of the 0-point motion, we are not squeezing, so we have states of the order of 0 decibels of squeezing. If you increase by a factor of, this we call it excess size, okay, a bit as a teaser, extra small. So if we increase by a factor of 10, this would mean in motional squeezing or quadrature squeezing invariance to create 20 decibels of quadrature squeezing. And there are very few quantum systems that have been squeezed to that level. Maybe light and a bit of spin squeezing, but I think not even 20 dBs, around 15 dBs. So this is already just by a factor of 10. If we increase by a factor of 100, then this is 40 dBs. If we increase to factor of 3, 60 dBs. If we go to 4 orders of magnitude, this is 80 dBs. And if we want to increase 5 orders of magnitude, this is equivalent to creating a motional quadrature squeezing of 100 dBs, which is really impressive. And this shows, of course, the challenge of delocalizing a particle in a coherent way, or preparing one of these macroscopic superposition states, because this must be equally challenging to prepare 40, 60, 80 or so dBs, right? So that's what to some extent defines what macroscopic means in this context, and clearly shows that this must be challenging. So we know that the limitation we will have to prepare these states comes from the coherence. And while a levitated particle in high vacuum looks actually very nice, because that's the picture you might visualize, okay, I have this particle really in high vacuum, there is nothing, and it's very isolated. Of course, in reality, that's not the case. There are many things going on. The particle has some temperatures, it's emitting thermal radiations. Even if you are in UHV, from time to time you touch a gas molecule. Even if you use some forces or potentials, these forces will fluctuate, the potentials will fluctuate. You might couple to some field fluctuations from thermal background radiation, fields arising from surfaces. And there might be even other things that we don't still predict and that could generate some decoherence. So of course, one must be extremely careful in proposing and doing experiments aiming to observe this macroscopic quantum physics with these particles. So this is clearly a challenge. And we will not now discuss in detail all these sources, but I just want to emphasize that once you think about the coherence, in our opinion, there are 4 requirements that kind of are needed, in our opinion, to prepare these superpositions. The first one is that any experimental run aiming to prepare the superpositions must be fast, and by fast I mean that it has to be faster than the intercollision time with the gas molecule. And UHB, this gives you around 10 milliseconds of time to do an experimental run. So any protocol should be faster than that, otherwise this gas collisions so will decohere the state a lot. The second one is that we know that as soon as you have a laser on of so much power, 100 milliwatts, interacting with a particle, you scatter a lot of photons, and they provide a lot of information to the environment about the position of the particles. So you create very fast decoherence, especially when the state is delocalized. So for any protocol that you want to do, you must most likely be in the dark or be very careful with the use of laser light. Laser light is great to cool and measure, but if you don't want to measure the position, I think it's nicer if you don't use the light, or you just use it in terms of pulses and things like that. Third requirement, not so much on the coherence, but related, is that, of course, we need to certify that the state is delocalized in a quantum manner. So namely that you have squeezed the state in a quantum way. And we know that the best way to do that is actually to use nonlinearities that prepare some features in case the state was delocalized. And I always like to think again about the double slit experiment in that context. If you want, the double slit experiment that we are all familiar with can also be understood as having this process here before the 2 slits, where you just have a very coherent source, and then that you delocalize over large scales. And before the particle impinges the 2 slits, you already have a very large delocalized quantum state, but you don't know if it's quantum or classically delocalized. And therefore, what you do here is you just prepare a state by putting the 2 slits, because if you want, this is performing a measurement. If the particle passes through the 2 slits, then you prepare that state in case it's quantum, which is a beautiful textbook CAT state. And note that this is the CAT state that you prepare just at the moment of the particle impinging the 2 slits. Because you see, you have a probability here in the probability of X, you have a probability to be on the left slit and the probability to be on the right slit. And this could be classical or quantum, you don't know. You know whether it's classical or quantum by looking at the fringes in momentum. Because if it's quantum, you have these nice negativities here that create an interference pattern in momentum. So the quantum state has already been prepared, or before the 2 slit, because it was delocalized. Here you prepare the superposition. Now all what comes after the double slit here is to certify whether this was quantum or not. Why? Because unfortunately we don't know how to measure momentum directly. Otherwise we would measure momentum here and we would get interference pattern. We only know how to measure position. If you measure position here, you don't know. So what comes now is free dynamics, which, as we showed before, it just squeezes the phase space distribution, and by squeezing it, you basically map the fringes in momentum into position, which is then what you see in the screen downstream. That's the case if you had fringes in momentum, right? So, and this, I want to explain it and spend some minutes here, because a bit surprisingly, you will see how this pattern appears again in our protocol in a bit surprising way. So this is the idea. You prepare a sufficiently coherent source, you delocalize it, you prepare, and then you certify that you delocalized quantumly by preparing a non-Gaussian state. Typically, this non-Gaussian state has fringes in momentum, and then you have to map the fringes in momentum into position, in the position distribution, so that you can measure it. Okay? And last but not least, the 4th requirement is that you must make sure that your experiment is repeatable, because you need to collect enough data. Like in the double slit, you need to repeat the experiment many times so that you get enough data points. And here I just to remember that, you know, experiments can be really not repeatable and not accurate. This is the worst scenario. Experiments can be accurate but not repeatable. Experiments can be not accurate, but repeatable, and that's already enough. If they are repeatable, I don't mind. It doesn't matter if they are not at the right place where I want it to be, provided they are repeatable, probably any quantum feature we will still see, right? So that's really the requirement, repeatability. And this is relevant, also connected to the first point of fast experimental runs, because experiments are very hard to repeat if they take very long. So if you need to collect data over hours, it's very hard to make the experiment stable over this long time scale. So we visualize experiments doing microscopic quantum superpositions to maybe last 1 second or 2 seconds. And in these 1 or 2 seconds, we will of course need to make 20,000 experimental runs, but everything should be done in a second so that you can be really stable and low frequency noises will not kick in and all these type of things. So that's why this, in our opinion, these 4 requirements are kind of important. Once you have this clear, which we know this is challenging, but what is useful is then you can start to exclude ideas, and we have excluded ideas we had in the past because they will not fulfill this. And then, you know, this allows you to maybe find ways to get ideas that at least fulfill these requirements, and that's what we actually have done in these 2 recent proposals. While they look very different, so a priori they look like these are completely 2 different ways to do the thing. Once we understood what is going on, there are some very interesting connections between the 2. So today I will just mention that one, which has to do with dynamics in a non-optical potential, whereas the one below has to do with dynamics with using short pulses of light. But let me tell you that one, right? So here the idea is we have a particle trapped with a standard optical potential, and in the background there is this dark here potential, which is in principle non-optical. And this is white, okay, in the sense that it's pretty big. It's a double well potential. It's so big that I actually don't look at the other side. And to parameterize the problem, so the optical potential is just a standard harmonic potential that is shifted from the top of the double well potential by amount xs. And the dark double well potential is a standard double well, so minus inverted plus quartic. So I define it here with 2 parameters, the small omega that tell me the frequency kind of this inverted potential here, and the quartic wall that has a distance capital D. And I define here, and while a particle in a double well potential is something that is super studied in quantum physics, we are interested in a regime that is not standard in quantum physics. This is this white regime in which basically this distance capital D is much larger than the initial wave function. And also this frequency here of the optical trap is larger than the inverted one. In this parameter regime, there is no tunneling of the particle to the other well. This is very, to some extent, almost classical type of dynamics, actually. And this is what motivates the idea, because what we would expect that now, if we turn off the optical potential, and in the background there is this nice double well potential, then what the particle will do is the following. First, the particle will start to move to the right. And while it moves to the right, it feels this inverted potential here that delocalizes the wave function exponentially fast in time. And then, so this, it goes, expands, and then it feels the quartic wall and it bounces off. And we know from quantum physics, when a wave packet bounces off of a potential, typically there is interference happening. So we expect interference. And then the nice thing is that the particle then, of course, will go back to the initial position where I can turn on the light again and cool and repeat the experiment. So you see it fulfills this repetition idea. And this is convenient because, it's, if we think about the double slit, we don't want to throw a particle into a screen and have to throw a new one because the particle is different and so on. It takes a long time. So here we like that everything is happening in the same trapping or in the same volume where there are the potentials. So I can, with the same particle, maybe repeat this protocol very fast. So this was the intuition. But of course, it was a challenge to analyze this because this is a very interesting parameter regime. And actually, we had to develop some numerical tools to do this. So the first one is explained here. We had to, to solve these dynamics, even though this looks very simple, one particle in 1D. This is actually, if you want, we need to calculate the Wigner function evolution because we want to account for the coherence in a parameter regime where there is a big phase space area, but we also need very high density to be able to capture all the narrow quantum features that might appear. So big volume, high density means a lot of grid points, so completely inefficient. So we had to develop here a tool where there's a time-dependent phase grading that follows the state using the classical trajectories of every phase space point, and this was actually very useful. And once we had these numerics and we saw the states that we were generating, we realized, okay, this looks very analytical. And it was afterwards when we saw the results that we could derive some semi-analytical tools to actually derive and understand what was going on. And this was just useful, not from a, let's say, intellectual point of view, but you know, having these semi-analytical tools are very useful because it allows us to optimize and parameterize the problem and experiment and so on, and this is very useful. So let me then show you what is going on. So the first thing you could do if you let the particle evolve in this potential is to calculate the mean value, x and p, and then you would see that you get this trajectory which looks like an avocado. And it has this an avocado. If this would be an harmonic oscillator, it would be a circle. Because of the non-harmonicities, this is not a circle, it's a bit deformed, and it has this avocado. Note that in the regime where we are, if you take the mean value of x and p, or you calculate the classical trajectory for a point particle starting at the same point, it's basically, in these scales, you don't see any difference. That's a signature of semi-classical dynamics. So the interesting part is what is going on with the fluctuations. Okay, so that's the mean value, but what is going on with the fluctuations? And that's what we could do with these numerical tools. So for instance, at this time, you start with the initial ground state. This is, you know, in units of zero-point motion, that's a standard ground state of an harmonic potential. And now we let it evolve. And at this time scale, you already see you start to squeeze a lot, okay? Because the x scale now has changed by 3 orders of magnitude, whereas the p scale is the same. So you're kind of squeezing already a lot. So if all of this would be Gaussian dynamics, the only things that could happen is just a squeezing and rotation in phase space. But because there is non-harmonicities, now this phase space distribution actually already at this point kind of bends, okay? And this prepares these states that are bended. And if you're familiar with that, I don't zoom in here, but you should expect that here there should be a lot of negativities. But these negativities, once you integrate, will be in momentum, like in the double slit, right? So this will not be happy. That happens at the bottom of the double well. But the cool thing from here to there is that there is a rotation in phase space. And then at this point, at the turning point, you have this beautiful quantum state, which you already anticipate that it will have fringes in the position interference pattern. And this state is actually, you know, that's what we found from the numerics, and you see that this looks like very analytical. Actually, this is what is called a cubic state. That's the state you generate by applying a cubic phase to a squeeze state. This is very well known in quantum information theory with continuous variables. And that's what is happening. Yeah, this is kind of a double slit type of experiment. And the cool thing is that now from here to there, it kind of, you almost do time inversion. So you go backwards. You know, you go here, but not completely because that's non-linear dynamics. So there are no revivals. So when you go back to the initial point, you have a state which actually it's also like a quartic state. It's these helix states that you obtain if you apply a quartic phase. And this makes sense because to some extent, when you come here, you accumulate a cubic phase. And when you go backwards, you kind of cancel the cubic phase. So what is left is the quartic phase, which is the next order in the potential. And to get a feeling of the dynamics, there is this video that shows the same. This is the state just going to the right in linear time scale. You know, so it just gets a squeeze. It gets at the bottom of the double well, turning point, and then it goes backwards. Okay, so and all the time that it takes to go from there to go back, this is given by Tm, which we can parameterize, and you can make sure this is smaller than the intercollisional gas molecules. And this is what is happening, and that's why I mentioned in the first part of the talk this idea with the double slit, because this looks very similar. You start from a coherent state, you expand it here, you delocalize it, then here the nonlinearities come that create non-Gaussian state with interference pattern in momentum, and from here to here you map it to position. You know, so there is this nice analogy with the double slit experiment. And the cool thing with the semi-analytics is that if you now calculate how much you delocalize in units of 0-point motion, you go up. This is at the at the bottom of the double well. That's when it's maximally delocalized. And then it compresses to the turning point, and then it goes kind of backwards. And this is kind of numerics versus analytics, so we understand these things. And actually, you see that how much you delocalize now is parameterized by this simple parameter, which is the ratio of the two frequencies of the harmonic potential and the double well inverted frequency, and the distance over how much you displace from the center. And this is valid in the regime where x cannot be zero. And once you have this, then it's very easy to parameterize the problem so that you can decide, okay, if I need to squeeze 60 dBs, or so that is 3 orders of magnitude, 4 orders of magnitude, or 5 orders of magnitude, that's the type of potentials I should use. And that's what I told you before, that this is very useful to have this semi-analytics so that you can do this type of stuff. Because if you would need to do this numerically, these simulations are painful, especially when there is decoherence, they're a bit slow. So that's quite nice, right? So all of this was without decoherence. So what we do next is to first see how we certify that we can do this, and how robust then the experiment is in terms of decoherence. So while there will be different ways to certify this type of dynamics, of course, the most beautiful one in terms of analogy to the double slit would be to really measure here at the turning point, because then you would have a position interference pattern. Okay, and indeed, what then we can do is we can solve the dynamics in the presence of the standard source of decoherence for nanoparticles that accounts for recoil heating, fluctuations from the potentials, thermal radiation, and so on. It's capital gamma here, which is in units of the zero-point motion, so that this is hertz. And then you solve the dynamics in the presence of noise, and then you get an interference pattern. So that's the marginal imposition. This is this ID function. Actually, from a cubic state, you get an ID function. And then you see that, of course, if you increase the coherence, then the visibility goes down up to nothing. Yeah. And what then you can do is you can plot actually visibility of this interference pattern as a function of amount of decoherence in units of the harmonic frequency, which is typically 100 kilohertz. And I like this plot very much because it shows first the dots are numerics and the lines are analytics, semi-analytics. So you see there is a very good understanding. And then you see that, for instance, if you want to squeeze 60 dBs and prepare these microscopic states of 60 dBs, you need decoherence rates of around 10 to the minus 7 in units of the trap frequency. If you want to increase 20 dBs, you need to increase 2 orders of magnitude the level of isolation so that decoherence goes down to 10 to the minus 10. If you want to go to 100 dBs, which is delocalizations of 10 to 100 nanometers, you need really these numbers of 10 to the minus 13. And then, of course, the scaling we know from this decoherence, and typically the scaling of decoherence also grows quadratically with the amount of squeezing. So if you increase eta by a factor of 10, then decoherence is increased by a factor of 100. So that's kind of expected from this dimensional analysis here, but it's nice to see the exact prediction. So if we want to do this experiment and squeeze 60 dBs, we need, that's a necessary requirement, not sufficient. We would need that this amount of decoherence of the order of 10 to the minus 7, which is kind of, I guess, the limit for thermal radiation, if it's at room temperature, so on. And yeah, so, but you know, this is kind of common in any proposal. This is it always appears here in a way or the other. Of course, that's almost a definition of preparing a macroscopic quantum state, is that must be challenging in terms of decoherence requirements. So there is, and at least until now, I think as a community have not found way out to this, because I would say it's almost by definition, but who knows. Okay, so with that, I'm about to conclude, just to say that, of course, in this collaboration, in this image, basically all of them are experimentalists, so there are only few of us who are theorists, so they are pushing hard to do to try to make these things possible. It's of course challenging, but yeah, going back to the beginning of the talk, you know, whether we can prepare these nanoparticles into large superpositions or not. This is, of course, super exciting, especially in the context of this conference. But so far, we only are able to prepare states of the order of the zero-point motion and Gaussian. So it will be interesting to see if we can delocalize a lot, 60, 80 dBs. Whether the states are Gaussian or not, that's not that relevant, because once you have so much squeezing, almost all the states will become non-Gaussian, because once you have these things super squeezed, they bend very easily. So and we know this is for sure needed to be able to entangle particles with weak interactions. So yeah, so just quick update about control techniques that we consider to design this protocol. Then of course we know that the coherence is key, and then I told you a proposal that uses these techniques. Because of time, I didn't want to make a review of all the ideas. Of course, there have been here many talks. Here we are focusing just on using dynamics in a non-harmonic potential, but I think in the conference there are many talks about using the Stern-Gerlach type of ideas, where they use coupling to a two-level system. This is complementary, complements these approaches. So take a look at these things. If you see something interesting, reach to us. Also like to emphasize maybe in other communities that of course these protocols can be tested with other systems like single atom, single ion, atomic gases, even classical states, because at the end quantum dynamics is very similar to classical dynamics. You just add the negativities at the end. So also testing all these dynamics with classical states are also relevant, and of course very important, because then we would be able to measure the levels of noise once you don't have light, right? Because all the most of the experiments now that operate in high vacuum, they are limited by the noise created by light. So it would be nice to do experiments where you see noise that goes beyond light. To my knowledge, perhaps there has been this recent experiment in the group of Tracy, where they see this heating of a particle in a Paul trap at UHB, and they see that this heating, there is already heating, of course, coming from electric field fluctuations that is lower than the heating coming from laser light when there is laser on. So, and of course, it's key to now measure this and try to mitigate it, no matter what protocol you would like to implement in the future. This is now absolutely a top priority, I would say. So yeah, so with this, I think I will conclude just with a summary. And yeah, thank you for your attention. I don't know if you have questions.
Okay, so questions. I think Anupan has a question.
No, thanks, Oriol. It's a very nice talk. I really enjoyed it. So I have two questions. Maybe let me start with the first one. So the emotional cooling is fantastic, but the bulk is still very hot. Now the question is, the bulk is hot. How much does it affect in your scheme, the visibility part? So that's the first question. And the second question, what I've realized, actually I have to give credit, because in your setup, I could see that the decoherence rate, what you require, is far, far better than what we are trying to do in the case of the Stern-Gerlach one. In the Stern-Gerlach one, what we find is that the amount of control we require is amazingly strong. Like sometimes even the current fluctuation we require to get a visibility, very good visibility, maybe 1 part in 10⁻⁻⁻, even quite rigorous. So how come in your, I'm saying how come, but what goes into your setup where the decoherence rate is not so demanding? So these are the two questions I have.
Yeah, okay, for the first part, so we know that the back of the envelope estimate for what would be the decoherence rate due to thermal radiation typically gives you, that's a nice way to express it, in my opinion. You have this gamma over omega is 10⁻⁻10 times the temperature of the bulk over 300 kelvins to a power of 6, all right? So if you have room temperature particles, then this is 10⁻⁻10, you would be around here, where you can then delocalize 4 orders of magnitude, but it would be harder more. To go more, then you would need temperature to be much smaller than the room temperature, which for this type of protocols, when you use laser light, I mean, of course, as soon as you shine laser, it always hits a bit, so maybe it cools then when you stop it, but the average temperature is, at least for this type of experiments where you use laser light, it's not so obvious that you can go to cryo temperatures, right? So this is, yeah, but this has to be seen, by the way, because this is actually not so clear. This strongly critically depends on the properties of the silica material at this scale, so it's not obvious that this will be true, and of course, since there are these strong dependencies, this is also critical, I would say so. And then regarding the other problem, I mean, so yeah, so here to compare the two things. So if you compare how much you can squeeze, okay, then I would say the two should be the same, right? So of course, if in some of the proposals you go to more than 100 dBs, then of course you are increasing quadratically with that, right? Because there was a scaling at a square. So and for the numbers I here I'm using, I'm going to maybe, I start from 10 to the minus 12 meters. And then I put factors 3, 4, 5. If you would go to 1 micrometer scale or so, then of course you put 2 or 3 orders of magnitude more, which then scale quadratically. So then you go to these very demanding things. So I would say that in terms of squeezing, things must agree, because at the end it's the same thing. Regarding other requirements, I mean, something I don't talk here in the talk today, but of course there is the part of repeatability. That I think is in this slide, yeah, here, which actually, to some extent, I know this fundamentally connects with Humpty Dumpty type of requirements.
Exactly.
Because this is the repeatability, because for instance, here it shows that when you repeat the experiment, if you are not precise in the alignment of the potentials up to 0-point motion scale, then the visibility drops. So this means that if you repeat 20,000 experiments, you have to make sure you are dropping the particle with a precision of 10 to the minus 12 meters, right? This actually and I guess that connects also with these requirements of stability for the Stern-Gerlach type of experiments. This is of course also kind of equally challenging, I would say. Yeah. So this.
Thanks.
Okay, so I see that we have 2 more questions from our Zoom participants. We have Sugato Bose for a question.
Hi. Oriol, again, a very, very nice talk. So I'm going to ask you just a mathematical question. So your potential is x square and then x4, right? The double well. How did you manage to get this cubic phase gate? Is it through some kind of
Yeah, exactly. This was the surprising thing, right? That we also, but you see, once you understand it, you will see it's actually not so surprising. But of course, this looks like that when the potential is centered at the bottom. But when the particle moves, the particle is seeing the local potential. And of course, then there are regions here where if you would do a Taylor expansion of this potential around here, you have the cubic. You have the cubic terms that dominate, because this is the first non-harmonic term that dominates. And so locally, the particle, and this is actually something we like, is that locally the particle is seeing a time-dependent potential. So first here it sees an inverted potential, then as soon as it moves, so while the potential is static, from the frame of the particle, it sees a time-dependent potential. And then you see the connection with this, because this uses a time-dependent pulses, which surprisingly from the body frame of the particle here, it looks like you are also implementing like a cubic potential pulse.
Interesting. So can I ask a very, very quick related question to the same thing? So now this excess cube you are using to give this momentum interference, right? And then the remaining part you say is translating it to position, right? So, but momentum also translates to position just even by free motion, right? For stretching long. Wouldn't that give larger separation between the momentum fringes? Like if you just let it go after, it will become time dependent. I mean, you have to change the potential in situ.
Correct. Yeah, so you could think here to say, okay, I have at this point here, I have this state with momentum, so I turn off everything and I let it do. This should work. But somehow what we like about doing everything within the potential is also because we like that the particle goes back to the initial place, so we can repeat for free. And also because ideally, if this is done ever experimentally, this non-harmonic potential that could be done electrostatically, we would like it to be as stable as possible. So, and typically if your potential, you don't need to turn on, turn off, you can make it more stable. So we kind of visualize having this background potential always on, which is very weak. When you put the light dominates, but when you turn off, the dynamics is dominated by the background.
Okay. Thank you very much. Yes. Thanks.
Okay, so unfortunately we have reached the deadline. So later you can ask more questions for Oriol by other means. So let's thank our speaker again.
Thank you. Thank you very much. Enjoy the meeting. Thank you.
Okay, so now